Hello everyone, welcome back to the channel. We're working on path tracking for Automated Parking Assist APA or Automated Valet Parking AVP. The Kinematic Bicycle Model KBM is the most effective model for expressing low-speed vehicle behavior. The KBM state equations that you normally see aren't simple formulas in the global coordinate system, but write a complex matrix field with trigonometric functions and curvature, like this. This is the result of transforming KBM from the global coordinate system to the FS coordinate system. In the previous episode, we introduced the global coordinates, body coordinates, and FS coordinates. If you don't fully understand their relationships, you can check out that previous video first. In this episode, we are going to build the state space. Let's change to a new chart. Let's establish the state space. Here, we select 4 states: FPY, state F, FPX, and speed V. FPY represents the lateral arrow. This is the vehicle's center of gravity, CG, and this point is the closest point on the reference trajectory. So this line between these 2 points is FPY. The main goal of MPC algorithm is to compress this value down to 0. Next, state F. State F is the heading arrow. This line is the vehicle heading, and this point on the reference trajectory, the tangent direction of this point is this line. This is also the XF axis in FS coordinate system, and this line is parallel with XF. So, state F between these 2 lines is heading arrow. Controlling state F ensures the front of the vehicle always follows the direction of the road. By the way, state REF. This line is parallel with XG in the global coordinate system. So theta F between XF and XG. Okay, next, FPX. FPX is the longitudinal displacement along the trajectory. Actually, this is FPX. This parameter represents how far the vehicle's projection point has traveled along the reference path. Since the road curvature changes continuously as we drive, the controller must know the current FPX to look up the corresponding curvature from the reference path points provided by the planning layer. Well, last is the speed of the vehicle, V. Why including V as a state? This V acts as an amplifier for the rate of change of the lateral and heading arrows. After understanding the state space parameters, we take their derivatives to establish the kinematic equations in the FS coordinate system. Here is the final result. First is FPY dot. Let me open a new chart. Okay. So this is XF axis and this is YF axis, and this line is parallel with XF. So FPY dot equals the direct projection of vehicle speed V on YF axis. So FPY dot equals V times sine beta plus theta F. this angle. And next, fpx dot equals the projection of v on xf axis is vx, and vx equals v times cosine theta f plus beta. Note here, vx is not fpx dot. There is a coefficient d between these two terms. Let's see how to derive d. And here, this is the reference curve. This curve, reference curve. I draw it here. And this is the point. The tangential speed is fpx dot, which we want. And this is the radius, the center of the radius. R is the radius, and O is the center of the circle. Now, the vehicle is out of the circle, and it runs on the concentric circle. This is the CG. And this distance between CG and this point is fpy. Note here, usually, if the vehicle is out of the circle, the distance of CG and this point is negative. And the tangential speed of CG is Vx. This is Vx. So, the Vx over Fpx dot equals R minus Fpy over R. It equals 1 minus 1 over R times Fpy. So 1 over R is curvature, rho REF. It equals 1 minus rho REF times Fpy. This is same with the coefficient d. It equals d. So the fpx that we want equals vx over d. And vx equals this equation. So the fpx dot finally equals v over d times cosine theta f plus beta. The same with the equation in the paper. Next is theta f dot equals, here first I clean the screen, and this line here is xg parallel with xg axis, so this is theta ref, and this line is parallel with xg, so this angle is theta ref. Theta f plus theta ref equals theta g. This angle is theta g. Theta g is vehicle's own yaw rate, yaw angle. This is vehicle's own yaw angle. And theta ref is caused by the bending of reference trajectory. So this is your angle bending by reference trajectory. Okay, so theta f dot equals theta g dot minus theta ref dot. And what is theta g dot? This is yaw rate. Let me clean the screen. I use this diagram. So this radius is r prime. This is r, and this is a kinematic augment model. And this is the rear tire. This is the front tire, and this is the speed V at this speed. And this is the slip angle beta at the CG of the vehicle. So this delta is the steering wheel, and this angle should be beta. And here, sine beta equals LR over R prime. And as we know, this is yaw rate. Theta G dot is yaw rate equals V over R prime. So this can be, let's delete R prime. So the theta G dot equals LR times sine beta over V. Okay, next, theta REF dot. Theta REF dot is the point at the tangential speed. So theta REF dot equals rho REF, the curvature of the reference trajectory, times FPX dot. This is what we derived just now. So substituting the FPX dot equals V times rho REF over D times cosine theta F plus beta. So this equation goes to LR times sine beta over V minus this equation. So this equation, so the theta F dot is the same with the equation in the paper. The final parameters is V dot, the speed of the vehicle equals acceleration A. This is simple. So now we form the seemingly complex non-linear state equations from the paper, like this. This is the complete state space of the kinematic bicycle model, transformed from the global coordinate system to the FS coordinate system. Because this model doesn't introduce dynamic parameters like the cornering stiffness, it is primarily used for path tracking in low-speed scenarios such as automated parking assist or automated valet parking. So, how do we establish the FS coordinate system state space for the dynamic bicycle model used in high-speed driving? We will explain that in the detail in the next episode. Thank you very much.